Okay.
And we're good to go. You've got it, Vipin and Z. Go for it.
Yeah.
Okay.
Over to you, Zay. Yeah, we got some.
So let me just get it started. Go. Hello, everyone. Thanks very much for inviting me here. And I'm Zi Zhou. I'm from the James Watt School of Engineering, University of Glasgow, and my supervisor are here, Coyote and Lei Zhang. And our group focuses on the wireless blockchain network. And the topic of the presentation is AI and blockchain-enabled future wireless network. This is the outline of the presentation. First of all, I'm going to introduce the challenges faced by the wireless network. Here are some the problems of the wireless network. The first one is network congestions. Nowadays there are more and more wireless users, so which exert a lot of pressures on the wireless network and cause a lot of congestions. And second is the security. The current wireless network is operated by the central server, which is owned by the several network operators. So once one of the server is compromised, which means the security of the user's data is also compromised. And with different device and such amount of the mobile users, the management and optimization of the wireless network is another problem. And with so many users, the spectrum is limited. So to find the best solutions for the spectrum management is also very hard. And set up the trust among the users is another challenge. And with 5G, it's an increment for the operators to provide different slicing to different users with different requirements. For example, for the video game, the network should be low latency, and for the live streaming, the network should be with high bandwidth. And secondly, I'm going to introduce some fundamentals of the blockchain and AI and how will interactively to provide solutions to the wireless network. First of all, let me introduce the fundamentals of blockchain. What is blockchain? And as we can see here, this is block, this is chain. So the blocks are the chained. This is a very simple term to interpret the blockchain. And in general, blockchain is a distributed ledger that operates in a peer-to-peer network with without the involvement of a third party. And as we can see here, the different the color of the little man are called nodes, and all the node has access to the blockchain. So the blockchain has characteristic of the uh, distributed and decentralized, and also every node has access to the blockchain, so it's fully transparent. And once the blockchain is generated, nobody can change it, so it's also immutable. This is how blockchain works. If a node here wants to initiate a request, and he wants to append the request to the blockchain, or the transaction to the blockchain, the request should be initiated to the wireless to the P2P blockchain network. This is the blockchain network. As we can see that every node here are interconnected. which means they can communicate with each other directly. And also every node has access to the blockchain. And before the transaction is appended to the block, there are two separate procedures. The first one is the generation of the block. The new block is generated according to the consensus mechanism in the blockchain network. And before the transaction is appended to the blockchain, to the block, the transaction must be validated by the network. Once the validation is gone through, the transaction can be added to the block, and the block will be added to the blockchain. And everybody has a copy of the blockchain, and the transaction on the blockchain can never be changed again. So in this way, the transaction is secured. And we have mentioned here the consensus mechanism, which is a fundamental of the blockchain technology. But what is consensus mechanism? In general, consensus mechanism can be categorized into two types. The first one is proof-based, such as proof of work, proof of stake. The most famous example of the proof of work is Bitcoin. And the proof-based type of blockchain has the characteristic of high scalability, no transaction rate. For example, in the blockchain, the transaction is generated every 10 minutes, which is quite low. And it requires computational power or concept of monetary. For example, in the Bitcoin, the miners or the node has to compete to compute the hash value, which consumes a lot of computational power. And in the proof of stake, instead, nodes will not compete to compute. They will deposit some stake into the stake pool. And the nodes will be selected according to the percentage of the stake they own in the pool. So in this way, it avoids the computational competition and solves a lot of power. And last, the proof-based is usually public, which means every participant or node can join the public the proof-based blockchain network. In contrast to proof-based, we have also voting-based. The most two famous cases are here, which is PBFT and Raft. As the name suggests, the voting-based blockchain reaches the consensus through the voting, so it has a high transaction rate, and as the consensus is reached through the voting, so it requires no computation. And but because the process involves a lot of communication to reach the consensus during the voting process, there is a huge communication complexity, so it's poorly scalable. And usually the voting-based blockchain network is private or consortium, which means the participant needs permission from the authority to join in the private blockchain network. So here I'm going to introduce what blockchain can do. First of all, blockchain can bring incentivization. It has immutability. It is transparent. It's distributed. It is decentralized. And it has smart contracts. With all the traits or the building function mentioned here, blockchain is able to solve those problems in the awareness network. Like the problem, it can provide problem traceability. Once the problem happens in the awareness network, since every transaction in the network will be recorded in the blockchain, people are able to find the problem according to the transactions. In this way, the problem can be traced, and it can provide storage of the data in the blockchain, and the data in the blockchain cannot be changed, and it's immutable. In this way, it provides data security to the wireless network. And with a smart contract, which is the predefined conditions in the blockchain, once those conditions are met, it will be enforced automatically by the blockchain. So in this way, blockchain is able to provide automation to the wireless network. And also it can provide spectral management. Oh, sorry. They're identical. Sorry. They should be the same. And as I have mentioned before, there are private or consortium blockchain where the participant requires the identity check and permission from the central authority. So blockchain is also able to provide access control and anomaly detection. And here I'm going to introduce the fundamentals of AI. AI in general can be referred to as machine learning. And machine learning has three types: supervised learning, unsupervised learning, and reinforcement learning. The difference between the supervised learning and unsupervised learning is if the data is labeled. The supervised learning use labeled data to train the model. So, for example, if we want to let the machine know the image of the dog, we just input a lot of photos with dog to the machine, and the machine will find the similarities between the dog. So once the model is trained, in the future we put another image of the dog to the machine. The machine can tell if this is dog, but this is a dog. But if we input an image of a cat, the machine will tell, no, it's not a dog. And here we have the unsupervised learning. In this way, in contrast to the supervised learning, unsupervised learning use unlabeled data sets, so which can be random. But this kind of learning is able to find the pattern among those data. So it is usually used for the clustering. And the third one is reinforcement learning, which is different to the previous two, which does not require the data set. Reinforcement learning enables the machine to interact with the environment actively to get the maximum reward in a long term. So reinforcement learning is usually used for the interaction and control. And here are some typical algorithms of different machine learnings. And here I'm going to introduce what AI can do in the wireless network. And first of all, I will introduce the traits of AI. First of all, AI can bring learning, adaptability, pattern recognition, automation, decision making, reasoning, and generalization to the wireless network. And with those traits, AI is able to provide proactive caching, power allocation, bin alignment, and routing and data trading, which is facilitated by the learning, adaptability, decision making, and automation of AI. And also AI can provide network slicing, handoff, and autonomous network management, which is facilitated by the pattern recognition of AI and decision making and automation. And in this part, I'm going to introduce the roles of AI and blockchain in the wireless network. This is a relationship between AI, blockchain, and wireless network. First of all, I'm going to introduce how AI and blockchain can benefit to each other. Blockchain can provide the data security to the AI, as we have mentioned before, and automation facilitated by the smart contract, and transparency and governance. And also, it enables data sharing, as the blockchain network is a P2P network. So it enables the data sharing among the users. And in return, the AI can provide intelligence to the blockchain. For example, it can make the smart contract even smarter. And AI is able to find the pattern, so it can provide the fraud detection ability to the blockchain. If a node behaves abnormally, AI can find it. So in this way, it can prevent any potential fraudulent activities. And also, AI is able to make some predictions based on the current and the past data input to the model. And also, AI can provide autonomous decision making to the blockchain. And combined AI and blockchain, it can enable the applications and unlock the potential of the wireless network as shown here. First of all, AI and blockchain can enable the data marketplace. As we have known that the wireless network will generate a lot of data, but most of them is not used properly. So with blockchain, the data can be unified and secured. So in this way, data can use the data secured and generated from the wireless network to train the model. And in return, the blockchain and wireless network will benefit from trained model from the AI. And the second is resource sharing. As we have known before, the blockchain enables the incentive, like in the Bitcoin. The miner who solve the hash problem will get the incentive. But in the Bitcoin, the contribution is computing power. But if we use the resource sharing as a competing, the node who shares their resource will get the incentive. So in this way, the users are more willing to share their resource, and data can learn the pattern of the resource sharing. So it enables the resource sharing in a dynamic way. And also, blockchain and AI can solve the network traffic problem, as the blockchain is a P2P network. So the nodes in the blockchain network can communicate with each other directly. So in this way, the pressure of the traffic is offloaded, and AI can learn the best way and provide the optimized routing for the traffic. So the traffic congestion will be reduced in this way. And also, we have mentioned that AI and blockchain can provide security, and due to the learning and decision making, AI can provide the management and the optimization, and blockchain blockchain's smart contract can also facilitate the management of the wireless network. And finally, blockchain can facilitate the data monetization and ownership of the wireless network. As we know that the most important part of AI is the data. However, the data is very difficult to be collected, as there is the concern that the data will be leaked, and the users who gave the data away will get nothing in return. But with the blockchain technology, it can encourage the users to share their data, and the data shared, the transaction will be recorded in the blockchain. In this way, the shared data is secured, and data is able to get more access to the data, and the model trained will be better. We have discussed the benefits of the AI and blockchain. Now I'm going to introduce some weakness and future directions for the AI and blockchain. First of all, the blockchain has a problem of the scalability, like in the private blockchain, where the consensus is reached through the voting. So once the network size is very huge, the communication complexity will be very huge, which makes the private blockchain less scalable. And second is the storage limitation, as every node has to get a copy of the blockchain, which consumes a lot of storage memory, which can be the bottleneck of the blockchain. And third one is supervision and governance. As a blockchain is a P2P network, there's no central entity to control the network, especially in the public blockchain. So once the development of the blockchain is uncontrolled, nobody knows what happens next. And the fourth one is power consumption, such as Bitcoin. It consumes a lot of power to compute the hash value. And the fifth one is appropriate selection of the consensus mechanism, as there are many different types of consensus mechanisms, and to use a consensus mechanism appropriately in different scenarios is very important. And the sixth one is attacks. The blockchain network is subject to different attacks, such as 51% attacks in the blockchain. Once the attackers controls more than 50% of the nodes, the blockchain is not immutable anymore. It can make any change to the blockchain as they want. As for the AI, the most difficult part for AI is the data collection. As the data is the best part, the most important part for AI. However, the data is very hard to be collected due to the concerns of the security and privacy. So if we can create the secure data collection platform, the AI will be benefited a lot. And second one is generic AI. There are different neural networks of the machine learning right now, such as the CNN and YOLO. For example, the YOLO is a very effective algorithm in the computer vision, especially for the facial recognition and objective detection. However, if we use YOLO to deal with other applications such as the language processing it will not do its job very good. And the third one is explainability of AI. This is a very big problem of AI. As we have know, AI is also known as a black box. The way we use AI is just simply to input something to the black box, and the black box will generate the outputs. But nobody knows what happens in the black box. So if we can create an explainable AI, I think it will be the revolution for the AI. And finally, is reinforcement learning limitations. As I have discussed before, the reinforcement learning interact with the environment directly. But the most use case for the reinforcement learning is in the game, because the environment in the game is secure and predictable. And the reinforcement learning application in the reality is limited, as the environment in the reality is unpredictable, which limits the application use case and deployment of the AI in the reality. And there are some here is some general overview of AI and blockchain for the wireless network. Next, I'm going to introduce some of my work, which is the deployment of blockchain in the wireless network. First of all, my work is to implement PBFT in the wireless network. But why do we choose PBFT? First of all, I'm going to introduce what PBFT is. PBFT is a consensus mechanism relying on voting, as I have discussed before. And the network is composed of two types of nodes. The first one is the primary, and the second type is backups, and rest of the nodes except the primary will be the backup nodes. And the consensus is reached through phase long case operations, which is prepare, prepare, and commit phase. As we can see that the process involves a lot of internal communications. So it requires a lot. It has a lot of communication complexity, and the PBFT network has a characteristic of high throughput, low latency, and requires no computing power. And most importantly, it can offer up to 1/3 fault tolerance. So this is a main reason I choose PBFT to be implemented in the wireless network, as the wireless network has some tolerance, has some faults, and PBFT is able to tolerate those faults. And here, first of all, I'm going to introduce the PBFT implemented by the IEEE 802.11 broadcast scheme. IEEE 802.11 is a short-range ad hoc network that use Bluetooth to for the nodes to communicate with each other. First of all, I'm going to introduce the transmission probability of different nodes, and the transmission probability tau can be calculated by this formula. And we have different parameters, which is Q, W, and PB. PB is the probability that the channel is busy, and which can be calculated by the tau and the number of nodes n. And the Q is probability that at least one packet is in the buffer to be transmitted, which can be calculated by this formula. The lambda here is a packet arrival rate. The ESTS here is the estimated time slot. So with those two parameters, we can get the probability that there's at least one packet in the buffer. And finally, this is the contention window size, and we have the number of nodes here. So with those parameters mentioned above, the tau can be transformed into this formula, which is a function of the lambda packet arrival rate, the window size, and the number of nodes. So with these three parameters known, we can calculate the value of the transmission probability in the IEEE 802.11 PBFT network. And with the transmission probability, we can get the success probability of the consensus, which is the success probability. And we can, as I mentioned before, the PBFT can provide up to 1/3 fault tolerance. Hence, more than two-thirds of the nodes should go through the prepare and commit stage to make sure the consensus is valid. So with the formula here, we can get the success probability of prepare and the commit stage, and then combine the prepare and commit stage, we can get the end-to-end success probability like this. Here are some results of the consensus success probability. This is the benchmark. As we can see, as the number of nodes increase, the transmission success probability decrease accordingly. And those lines stands for the different success probability in different phase. And in this figure, we want to investigate how different contention window size and packet arrival rate lambda impact on the performance of the network. As we can see here, it's very different. So later in these two figures, we want to investigate which parameters has more impact on the performance. So in this figure, we fix the lambda and use different value of window size. You can see that the performance is very different. And in this figure, we fix the window size and use different value of lambda. And the performance is different, but it's not as much as in this one. So we can reach a conclusion that the contention window size has a bigger impact on the performance of the IEEE 802.11 PBFT network. And there are another two performance indicators of the network, which is the confirmation delay and throughput, which is highly correlated. As the throughput is literally the reverse of the delay, like showing like here, and we can see that the throughput is quite high. We have discussed like I have said before, there are some limitations of the PBFT in the IEEE 802.11 wireless network. It has high communication complexity, low scalability, and low connectivity and the consensus success probability is low if the network size is huge. So here we proposed a solution to that, which is introduce a central access point to facilitate the internal communications among nodes, as shown here. There are different arrows. The directions of the arrows stands for the download or the uplink or downlink communication. And the color of the different arrows means the timing of the transmission. As shown here, we can see that the downlink has the same color and the uplink is different, which means the downlink is synchronized. The uplink can be asynchronized. And this is a diagram of the proposed solution as shown here. As compared to this figure here, we can see that in this part it's very complicated, which means the communication is very has a high complexity. And here is much simpler. So the proposed solution has lower communication complexity and much higher scalability and much higher consensus success probability. This is the result of the proposed solution. As we can see here, as the number of nodes increase, the consensus success does not decrease at all. It increases. Sorry. Also, in this figure, as the coverage rate is 80, the consensus success probability also increases as the number of nodes increase, which means that the proposed solution is more scalable in terms of the number of nodes, and this is the benchmark result from the IEEE 802.11 broadcast scheme. As we can see here, as the number of nodes increase, the success probability decrease. This is because that if there are more nodes in the network, the contention for the wireless channel is higher, and the chance that a collision happens is also higher, which leads to a lower success probability of the wireless PBFT network. And also there are two other performance indicators, which is communication complexity and average transmit power. As we can see here, the conventional PBFT implemented by the IEEE 802.11 increases exponentially, while the proposed solution only increase linearly. And this also applies to the average power. The proposed solution can achieve approximately 82.4% less transmission power, and the different color of the transmit power means the simulation or analytic result, and the perfect match between those two lines indicates that the analytical result is valid. And we have discussed the benefits of the proposed solution, and here are some drawbacks of it. The first of all is it will introduce some degree of the centralization, because the internal communication relying on the base station. It will introduce some centralization to the blockchain system. and it will lead to a lower security. If the base station is compromised, the message transmitted by the nodes will also have a chance to be compromised, and they will have to use a direct link again. And the third one is privacy leakage, as the message is transmitted by the base station. If a non-PBFT node is within the transmission range of the base station, it has a chance to capture the message transmitted by other users. So the privacy has a chance to be leaked. And the fourth one is a mobility issue. As the nodes can be mobile, if the node moves to a different cell of the base station, or moves out of the communication range of the base station, the nodes will be dropped from the network. So in this case, a roaming is therefore required, or the efficiency of the PBFT network will be reduced. That's all for today's presentation. Thank you.
Thanks. Thanks, Z. Thank you so much for this wonderful presentation. So, I have a few questions. As PBFT is considered as one of the best consensus mechanism for wireless, at least. So, did you guys also consider some other consensus, or means any particular reason you guys choose this only PBFT or not other consensus mechanisms?
The PBFT is only my interest, and we have another students who is studying the raft.
Oh, okay.
The same group, and the reason we choose the voting based blockchain is that as the awareness or the mobile users are usually computational restrained, which means they don't have much computing power to solve the hash problem, which is required by the Bitcoin. So we use the lightweight, the voting based consensus mechanism instead.
Mm-hmm. And you also considered some like a L2 solution or anything which can increase the scalability at least in this, because this is the same problem for any use case when we are using this PBFT or any other consensus mechanism in wireless domain.
Yes, I admit that the L2 could be another potential solution which can increase the scalability of the blockchain, but currently we are not studying that. But I think it could be a potential direction for us.
Mm-hmm. And any other use case you or your team is means working on, especially in the wireless domain, except this?
Because we are in the school of engineering, so we only use the blockchain in the wireless case.
Some other wireless, like currently, I think 802.11, that's what you are considering, right? Anything
Yeah,
specific on RAN or core or anywhere else or any particular? Just initially, you mentioned that we can use it in network slicing or other use cases.
Maybe there are some other people working on that, but I have no idea for now. I'm sorry.
That's okay. But thank you again. Thanks, Z, for accepting our invitation and this wonderful talk.
Okay, no problem. Thank you.
Thank you so much. So we'll share this link with you, right? This and I think let me ask Scene to Scene, you're here, right?
Yeah.
Yes, I'm still here.
Okay. So Scene, could you stop live and recording, please?